Hey guys, I'm going to be making a tutorial on how to solve this problem. It's a thermodynamics problem, and what we're going to be doing is we're going to be trying to calculate work. So an example of where you'd find this maybe is in a biophysical chemistry class. And so our question is, let's say we have a sample of nitrogen with a molecular weight of 28 grams per mole. So our sample of nitrogen has a mass of 21 grams and it occupies 18.6 decimeters cubed. Okay, so that's its volume at 298.15 Kelvin. Okay, calculate the work done when the gas expands. All right, so as I read through a problem, I really like to write down things that I see are important. So right here, when I see calculate the work done when the gas expands, when a gas expands, you know the work will be negative. So that's important. And we're going to calculate the work when we have isothermally until its volume has increased by 5 decimeters cubed. So decimeters cubed, this is going to be delta V. Delta V equals 5 decimeters cubed. Okay, and the conversion for decimeters cubed equals 1 liter. So 1 decimeter cubed equals 1 liter, and it also equals 10 to the negative third meters cubed. So this is going to be our standard units right here. So let's focus on part A. So part A, we have delta V, we have the molecular weight, 28 grams per mole, we have a mass of 21 grams, and we have a temperature of 298 Kelvin. So this is what I like to do. I like to write down everything that's given to us in the problem, and then I like to write down what we're looking for. So we're looking for work. So a key thing in this problem is that it tells you we're looking at it isothermally. So as far as work is concerned, when we're dealing with something isothermal, that means that delta T equals 0, but more importantly, it affects the work equation. So under isothermal circumstances, work equals negative nRT times ln of V2 over V1, just like that. Okay, so R is a constant, 8.13, or let's see, 8.314. T was given as 298 Kelvin, and N we don't know, but we have the mass of the sample and the molecular weight, so we can figure that out. So if molecular weight equals mass divided by moles, we can rearrange that to find moles as mass divided by molecular weight. Okay, so we have N, we have R, and we have T, and if we're calculating W, we need V2 and V1. So let's see what we can get for that. So a sample of nitrogen occupies 18.6 times 10 to the negative third meters cubed. So that's going to be our V1. V1 equals 18.6 times 10 to the negative third meters cubed. And V2, so if we know that it increased and expanded by 5 decimeters cubed, V2 will equal 18.6 plus 5, 23.6 times 10 to the negative third meters cubed. Okay, so then we can calculate work by plugging everything in. So work equals negative 21 grams divided by 28 grams per mole, and that will cancel grams, times R, which is 8.314 joules per Kelvin times moles, times temperature, 298 Kelvin. We can see that Kelvin cancels here, and this moles in the denominator actually flips up to the numerator, and that cancels with these moles, times ln of V2, which is 23.6 times 10 to the negative third meters cubed divided by 18.6 times 10 to the negative third meters cubed. Okay, and these should cancel. So we're left with just joules, which is what work is measured in. So if we punch all this into our calculator, we have this negative sign out here, so our value is going to be negative, and we also know that because work has or the gas has expanded. So we calculate this to be negative 442.4 joules. Okay. Also, a really important thing to note is that this problem was isothermal. So this is work isothermal. And whenever we have isothermal work, that is going to be reversible work. Reversible work. Okay. And an important thing about reversible work is that it's the max work. So this is the maximum work. When work is reversible and isothermal, that's the maximum. Okay? So part A is done. We've calculated work. Now let's do part B. Part B says, calculate the work done when the gas expands isobarically. So what does that mean? Isobaric means that pressure is not changing. So we're at a constant pressure against a constant external pressure of 79 kilopascals. So delta P, change in pressure, equals 0 at 79 times 10 to the third pascals. So we want our units in pascals. So this is good. So calculate the work done when the gas expands isobarically against a constant external pressure of 79 kilopascals until its volume has increased by 5 decimeters cubed. So again, volume is what's changing here. Delta V equals 5 times 10 to the negative third meters cubed. So all I did was take decimeters cubed to meters cubed, which we can see in this relationship right here. Okay, so what's next? We still have that temperature is 298 Kelvin. We still have the same mass, molecular weight, and everything, but what is important about part B is that the problem is isobaric. So in an isobaric circumstance, we have a different equation for work. So work equals negative PEX, or external pressure, times delta V. Okay, so PEX is just going to be the 79 times 10 to the third pascals, and delta V, it gave us directly in the problem what delta V was, 5 times 10 to the negative third meters cubed. So we can simply plug these values in. So negative 79 times 10 to the third pascals times 5 times 10 to the negative third meters cubed. And whenever we have pascals times meters cubed, we get an answer in joules, which is exactly what we want. Work is in joules. Also, what's kind of cool about this problem is we have times 10 to the positive third, and that will cancel with times 10 to the negative third. So that makes the problem a little bit simpler, and now we just have negative 79 times 5. And we get that is negative 395 joules. Okay, so this is exactly how you would do this problem. Part A, keep in mind that it's isothermal, so therefore it's reversible, and that is the maximum work. So our answers make sense also. Part A, work was negative 442.4 joules, and part B, we had a lesser value of negative 395 joules. All right, thank you guys for watching. I hope this helped you guys with figuring out these kind of problems. Thank you.